This video demonstrates a procedure for putting together a laser speckle contrast imaging, or LSCI, system capable of full field imaging of blood flow in small animals. This is accomplished by first setting up both a camera with an attached lens and a laser source that emits diffuse laser light evenly over the field of view of the camera. The second step of the procedure is to prepare a flow phantom or an animal with a suitable window for imaging the desired tissue. The final step of the procedure is to use software to collect images from your camera and turn them into speckle contrast values, ideally in real time. Ultimately, results can be obtained that show images of relative blood flow through laser speckle contrast imaging.
Hi, I'm Adrian Pontecorvo from the laboratory of Dr. Andrew Dunn in the Biomedical Engineering Department at the University of Texas at Austin. Today, we'll show you a procedure for building your own laser speckle contrast imaging setup. We use this system in our lab to study cerebral blood flow. So let's get started.
Laser speckle contrast imaging, or LSCI, is a simple and powerful technique that is used for full field imaging of blood flow. Diffuse laser light creates a speckle pattern, and the speckle contrast value quantifies variations in the speckle pattern that are related to the flow of red blood cells as they pass through it. To begin building the imaging system, mount a camera with a macro zoom lens to a vertical stage, or you could mount the camera to a surgical operating microscope. Now follow the appropriate directions from our website to download the software that will be used to control the camera. Place any object, in our case a simple business card, into the field of view and adjust the lens until it is in focus. You can run the software in live video mode to make sure your object is in focus. Next, set up a laser diode with a collimation kit and then move it over to your object to illuminate it. Turn down ambient light and adjust laser light so that it is evenly illuminating the entire field of view of the camera. Red laser light was used here to make things easier to see, but near-infrared laser light could also be used and has the additional benefit of penetrating deeper in tissue. If a near-infrared laser is used, make sure that your camera does not have a built-in infrared filter that would block the laser light. With the imaging equipment set up, let's see how to surgically prepare animals for experiments. Before the imaging system can be used, animals must go through a surgical preparation to create a window over the tissue of interest. This involves thinning the skull over the desired brain region. Begin by placing the urethane anesthetized animal into a stereotactic holder. Use a dissection microscope to remove the skin and tissue surrounding the skull. Now use a dental drill to thin the skull over the desired region until it is transparent. Depending on the experiment, the thinned skull can either be removed or simply left alone. Next, drill a small hole about 2 mm away from the window. This is done because the experiment later involves using a needle to prick the surface of the brain. Finally, use dental cement to create a well around the desired region and place a drop of oil or silicone gel into the well to improve visibility. With the animal prepared, let's see how to collect data. When collecting data, the camera software is used to acquire images and also calculate speckle contrast values. Place the animal into the field of view of the camera, and with the software in live video mode, adjust either the camera height or lens focus until the desired region is seen. Change the position of the laser diode so that it is illuminating the thin skull region, and adjust the laser power to make sure enough laser light is reaching the camera without saturating it. You should now be able to see clear images of the vasculature. Before you are ready to begin your experiment, select the number of images to acquire and how much averaging to do. Also select regions of interest you may want to monitor more closely. As data is acquired, relative blood flow changes can easily be seen by generating an image of changes to the speckle contrast value, or by monitoring the speckle contrast values in the regions of interest. In this experiment, pricking the surface of the brain with a needle induces a large increase in blood flow, typically associated with cortical spreading depression.
We've just shown you how to build your own laser speckle contrast imaging system and use it to image cerebral blood flow in vivo in real time. When doing this procedure, it's important to remember to test your system on something simple like a business card to make sure your image is in focus and that your laser light is evenly illuminating your field of view. So that's it. Thanks for watching and good luck with your experiments.